neck. The neck consists of the funnel or vent filled up with the hardened lava of the last eruption. The diamond mines of South Africa are in almost cylindrical pipes, which are cut through stratified rocks and are filled with an irregular agglomerate. On the surface, the pipes show no topographical indication of their presence, but are quite level with the ground. Lava flows and sheets, which were poured out on the surface of the ground, may be recognized at a glance and traced to the vent whence they issued. Fragmental products are positive proof of volcanic action, for they cannot be formed underground. The plutonic rocks form a series which no one has ever observed in the course of formation because they were solidified at greater or less depths underground. Though these unstratified masses cannot be observed in the process of formation, as may the lavas and pyroclastic rocks, yet the nature of the rocks themselves and their relation to the volcanic and stratified rocks afford a satisfactory explanation of themselves. A primary division of the plutonic masses is into 1. Injected and 2. Subjacent bodies. An injected body, says R. Daly, is one which is entirely enclosed within the invaded formations, except along the relatively narrow openings to the chamber where the latter has been in communication with the feeding reservoir. Subjacent bodies, on the other hand, have no floor upon which the intrusive mass rests, the communication with the Earth's interior being by great openings, which enlarge downward indefinitely within the limits of observation. Injected bodies are of manifold variety of shapes and sizes, and differ in their relations to the enclosing or country rock, and different terms are accordingly used to describe them. A dike is a vertical or steeply inclined wall of igneous rock, which was forced up into a fissure when molten and there consolidated. Dikes of a certain kind may actually be seen in the making, as when the lava column of a volcano bursts its way through fissures in the cone. Intrusive veins are smaller and more irregular. Frequently branching fissures which have been filled with an igneous magma, they may only be a few inches in thickness and may often be traced to the mass which gave them off. Sills or intrusive sheets are horizontal or moderately inclined masses of igneous rock, which have small thickness as compared with their lateral extent. Sheets conform to the bedding planes of the strata, often running long distances between the same two beds, but if they can be traced far enough, they may generally be found cutting across the strata at one point or another. In thickness, they vary from a few feet to several hundreds of feet. The Palisades of the Hudson are formed by a sheet of unusual thickness. Its outcrop is 70 miles long from north to south, and its thickness varies from 300 to 850 feet. A laccolith is a large lenticular mass of igneous rock filling a chamber which it has made for itself by lifting the overlying strata into a dome-like shape. The magma was supplied from below through a relatively small pipe or fissure. The rock of which laccoliths are made is nearly always of the highly siliceous and less fusible kinds, so that it can more easily lift the strata than force its way between them. Batholiths are great masses of plutonic rock, hundreds or even thousands of miles in extent. In general characteristics, they agree with stocks, except for their very much greater size. Granite is the commonest batholithic rock, and in such masses forms the core of many great mountain ranges like the Sierra Nevada and the Rocky Mountains. Much has been said of the manner in which rocks are cut down and built up again by the destructive agent of atmosphere and water, but there is another force which has led to the transformation of a rock from its original form, and this is known as metamorphism. The term is somewhat vague, for so many factors entering into the making of metamorphic rocks, and the process took place so many eons ago, that it is all but impossible to gain a clear conception of the manner in which they have come into being. An increase in hardness and in the degree of crystallization occurs, and not infrequently includes the generation of an entirely new set of minerals, characteristically arranged. Whether the original of the rock so metamorphosed was igneous or sedimentary cannot always be determined. Metamorphism, as classified by Scott, is of two quite distinct kinds. 1. Contact or local, and 2. Regional metamorphism. Contact metamorphism, he says, is the change effected in surrounding rocks by igneous magmas. There is a difference between the effects produced by a surface lava flow and those caused by a plutonic intrusive. In the former case, the results are usually not very striking because of the way in which a lava stream surrounds itself with non-conducting scoriae, and are such as may be referred to the action of dry heat. Bituminous coal is changed into a natural coke by the removal of its volatile constituents. Clay may be baked into a hard red rock looking like earthenware, and limestone changed to quicklime by driving off carbonic acid gas. Plutonic intrusions are more efficient agents of change because they are presumably of a higher temperature and retain their heat longer, and because the vapors and gases which they contain cannot escape into the atmosphere but strongly affect the invaded rocks. The rock invaded and metamorphosed may be either sedimentary, igneous, or already metamorphic, and the effects may be very marked or surprisingly small. Indeed, it is often quite impossible to say why the changes should be so insignificant. The distance to which the zone of change extends is wider when the intrusive mass cuts across the strata than when it follows the bedding plane, so that a dike or stock is more effective than a sill. Contact metamorphism, as its name implies, is a local phenomenon, but a widely ramifying and complex system of igneous intrusions may change large areas of sedimentary rocks. Regional or dynamic metamorphism applies to the reconstruction of rocks upon a great scale in areas covering, it may be, thousands of square miles, and evidently other processes in addition to those of contact metamorphism are needed to explain such widespread changes. Regionally, metamorphic rocks are, with the exception of the slates, thoroughly crystalline, and usually have lost all trace of whatever fossils and stratification planes they may originally have had. The first step in metamorphism consists in a mere hardening of the rock, accompanied with the loss of water and other volatile substances. In the second stage, the component minerals already present are crystallized, but new compounds are sparingly formed. The stage is frequently accompanied by cleavage, which, to distinguish it from that of minerals, is often called slaty cleavage. Cleavage, suggests C.R. Van Hise, is a capacity present in some rocks to break in certain directions more easily than in others, while fissility is a structure in some rocks by virtue of which they are already separated into parallel laminae in a state of nature. The term fissility thus complements cleavage, and the two are included under cleavage as ordinarily defined. Ordinary roofing slate is one of the best possible examples of a cleaved rock, and in beds of slate interstratified with other rocks, the cleavage is usually quite perfect in the former, absent or but partially developed in the latter. The causes of metamorphism have been summarized by W. B. Scott as follows. 1. Heat is evidently a very important factor of change, as is shown by the phenomena of contact metamorphism, and by numerous experiments by which the process has been imitated successfully. In contact metamorphism, the heat is derived from the igneous magmas, and in dynamic, it is in part mechanically generated, in part due to the interior heat of the Earth invading deeply buried masses. 2. Compression is believed to be the great agent of dynamic metamorphism, and the amount of the change depends upon the intensity of the compression and the depth at which it operates. Hence the varying results, ranging from gentle folding at one end of the series through violent folding to complete reconstruction, crystallization, and foliation at the other. 3. Moisture is another potent agent of reconstruction. Superheated water under pressure is able to attack and dissolve the most refractory substances and to build them up into new combinations. Many minerals, such as feldspars, which have never been artificially crystallized by dry heat alone, will crystallize readily in the presence of superheated water, and the water lowers the temperature necessary for metamorphism. Rocks which melt at 2,500 degrees Fahrenheit, dry heat becomes pasty at 750 degrees Fahrenheit in the presence of water. In contact metamorphism, steam is a very important factor of change, but other vapors and gases play an efficient part. 4. Pressure, as distinguished from active compression, is a necessity for any extensive metamorphic action, whether contact or dynamic. It is the difference of pressure which is responsible for the different effects of surface flows of lava and of subterranean intrusions, and which gives to depth its importance as a controlling factor. The deadweight pressure of overlying rocks prevents the rapid escape of the mineralizing vapors, and when sufficiently great, causes the rock to shear and flow without fracture. Limestone, heated at the pressure of the atmosphere in a lime kiln or an open vessel, becomes quicklime through the expulsion of carbonic acid gas. But, heated under pressure so that the gas cannot escape, it crystallizes into marble. Such pressure also is an essential factor in dynamic metamorphism, as a precondition in enabling the rock to behave more or less plastically under active compression and without shattering. Dynamic metamorphism must, therefore, take place at considerable depths below the surface. The non-foliated rocks represent the less advanced stages of metamorphism in which the forces of compression may have produced cleavage or fissility, but not foliation. The fissures, veins, and faults, which are to be found alike in igneous, sedimentary, and metamorphic rocks, afford an excellent opportunity for the intrusion into the rock of matter of a dissimilar character. Thus, waters-bearing mineral compounds in solution, passing over such crevice or fissure, might readily precipitate that which it bears each tiny grain of precipitated mineral forcing out water at the top. Sometimes these veins are filled in again with the same form of matter as that of which the main rock is composed, but different in structure. Sometimes the veins are filled by sediment which has been blown or washed in, and not infrequently fissures caused by earthquakes have been filled up from below by the intrusion of alien substances forced up by the interior pressure. Fissures thus filled vary greatly in dimensions, from a few inches to many miles in length. The minute veins are filled with material derived from the walls by solution and redeposited in the crevices, such as the veins of crystallized calcite in limestone. Great fissure veins, on the other hand, which may run unchanged for many miles and penetrate to depths beyond the reach of mining, are characterized, says Spur, by regular straight walls, by a fairly constant width, and by a definite direction of both strike and dip. A third class of mineral veins is composed of the veins of replacement, in which the circulating waters have not merely deposited minerals in an open fissure, but have gradually substituted one substance for another by dissolving out the latter and replacing it with the former. It may be molecule by molecule, so that the replacing minerals are pseudomorphs after the older series. A replacement vein represents a water channel of some kind, and so it has a more or less definite direction, but it seldom has sharply defined walls, for the new deposits impregnate the country rock and fade away into it. Replacement veins are most commonly found in limestones, since those are the most readily soluble rocks, but they also occur in rocks which are relatively very insoluble, such as sandstones, and in igneous rocks like granite. Frequently, the ores of the commercially valuable metals are found in mineral veins, which then are called metalliferous veins. Structural geology, says W. B. Scott, in summarizing up the questions relative to the formation of the rocks, brings vividly before one the innumerable changes through which the Earth's surface has passed and which are recorded in the rocks. The sedimentary rocks, originally laid down underwater in approximately horizontal positions, have been upheaved into land surfaces, either without losing that horizontality or being tilted, folded, compressed, or even violently overturned. Or they may be fractured and dislocated in great faults and thrusts. These movements have been found to be due to enormous lateral compression set up within the crust of the earth, a compression generated in some manner not yet clearly understood. Whether folding or faulting shall result from a given compression depends upon the rigidity of the strata, upon the load which overlies them, and the sudden or gradual way in which compression is applied. The results of compression on a large scale are accompanied by certain minor changes not less characteristic. Compressed rocks are cleaved, fissile, or schistose, according to the intensity of the action and whether the rocks affected are in the shell of flowage or of fracture. These changes may go so far as completely to reconstruct the minerals of the rocks, destroying the old, generating new, and obliterating the original character of the strata. Thus, displacements, dislocations, cleavage, fissility, and dynamic metamorphism are but the varying results of lateral compression acting under different conditions and at varying depths. Another class of rocks, the igneous, massive or unstratified, were found to have penetrated and overflowed the strata and to have consolidated in the fissures and cavities which they have made for themselves, or to have been poured out freely on the surface. According to the circumstances under which these masses have cooled, the resulting rock is of glassy, porphyritic, finely or coarsely crystalline texture. When solidified as sheets or dikes, the igneous rocks may be folded, faulted, cleaved, or metamorphosed like the strata, and when a region has been long and repeatedly subject to compression, its structure may become excessively complex and the metamorphosis of its rocks so complete that not even the most careful examination will suffice to distinguish those rocks which were originally sedimentary from those which were igneous. Highly heated waters circulating through fissures and along the joint planes of the rocks deposit the substances which form the mineral and metalliferous veins, though concerning the source of these substances and of the solvent waters there is much difference of opinion. Our study has taught us that many of these processes go on deep within the Earth's crust, and hence cannot be directly observed, but must be inferred from their results. Encouraging progress has already been made in this work, but very much more remains to be done before a knowledge of structure and its full meaning shall be even approximately complete. End of section 21.
Section 22 of The Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 2, edited by Francis Rolt Wheeler. Geology, Chapter 12, Part 1. Physiography. The topographical features of the Earth, the mountains, plains, and river valleys, present a striking appearance to even the most casual observer, and the question as to the cause of their present arrangement is one that naturally arises. It has been suggested that this subject treated from the geological side should be called geomorphogeny, since the geologist makes use of the topography to determine the nature of the changes, while the physical geographer employs the conception of changes to explain the topography. It will be seen immediately how the two subjects interlock, but nonetheless there is a quite different principle involved. The questions involved in geomorphogeny, then, are those of aggradation, or the elevation of the land, and diastrophism, the removal of land in one place for the purpose of building it up in another. A third class of factors, which, however, are passive rather than active, namely the character, arrangement, and attitude of the rock masses. A partially degraded region in which the rocks are homogeneous will have a very different kind of relief from one in which the rocks are heterogeneous and differ materially in their powers of resistance to the denuding agents. The topography of any region is the resultant of the very complex interaction of many different kinds of factors, and is subject to continual change according to definite laws. Suppose, in the first instance, a region newly upheaved from beneath the sea into dry land. The topography of such an area will be constructional, due entirely to the processes of diastrophism and accumulation, and characterized by the absence of a highly developed system of drainage by streams. The coastal plain of the middle and southern Atlantic states is an example of such topography, but slightly modified. Next, the processes of denudation begin their work upon the region. The sea attacks the coastline by cutting it back in one place and building it out in another until a condition of equilibrium is attained. Rivers are established, adjusting themselves to the structure of the underlying rocks and cutting deep, trench-like valleys, while the atmospheric agencies widen out the valleys, slowly wearing down and washing away the sides and tops of the hills. The details of the cycle of topographical development, which is essential in geomorphological reasoning, says Scott, differ widely under different climatic conditions. If we take the successive stages as they are developed in a pluvial climate, with all basins filled, abundant rivers running to the sea, and the snows of winter melting in summer, to constitute the normal cycle, we shall find that the arid cycle of desert climates deviates from the normal in very important ways. Assume the elevation of a large area with more or less of deformation. The drainage will be consequent on the newly formed slopes, and the lowest part of each basin will form the local base level, for the streams of each basin of deformation are confined to the basin and die away in the floor without uniting into a permanent trunk system. In the youth of the cycle, the highlands are slowly eroded, and deposition takes place on the slopes and floor of each basin, diminishing the relief and raising the local base level, a strong contrast to the corresponding stage of the normal cycle, in which relief is increased by the excavation of stream valleys. Even in arid regions, however, valleys are cut on the highland slopes, while the basin floor is made nearly level by deposition. This stage is exemplified by the Great Basin and its mountains. Water is the chief agent of erosion and deposition during the period of youth, but the wind is also important in eroding the bare rocks and in distributing the finer waste, part of which it carries outside the arid region altogether. Extremely slow as this process of complete removal of the finer debris by the wind undoubtedly is, yet it is the only agency which actually lowers the average altitude of the region, for no water flows out of the area we are considering. Maturity of development is attained by the connection of the separate initial basins into a continuous whole. Erosion of the highlands and deposition on the basin floors may result in the formation of a continuous slope from a higher basin to a lower one, so that, even in the absence of any permanent stream connecting the two, the rain will wash material to the lower basin and a new and lower base level will be established for the higher one, while the lower basin floor will be built up by the transfer to it of the waste accumulated in that which lies at the higher level. As the coalescence of basins and the integration of stream systems progresses, says W. M. Davis, the changes of the local base levels will be fewer and slower, and the obliteration of the uplands, the development of graded Piedmont slopes, and the aggradation of the chief basins will be more and more extensive. In maturity, the relative efficiency of the eroding agents is not the same as in the earlier stages. The wasting away of the highlands diminishes the scanty rainfall, and the quantity and efficiency of the water decrease with the diminution of relief. But the activity of the wind is not affected, and hence its relative importance is increased. The period of old age, continues Scott, begins with the breaking up of the unified drainage system through the excavation of wind-made hollows in the softer rocks, a process unlike anything which we have found in pluvial climates, where a drainage system once established is not disintegrated during the progress of a normal cycle. If the desert were strictly rainless and erosion carried on by the wind alone, there would apparently be no limit to the excavation of such hollows, but no such instance is known, and the occasional heavy rains suffice to counteract it by filling up the hollows, but the drainage system is effectively disintegrated, and the waste, which in the stage of maturity gathered on the lower parts of the region, is washed about irregularly. The surface worn down by the wind may have no slope in any particular direction, for the wind has no base level and is not affected by the inclination of the ground, but this surface may be reduced to an essential plain-like character. Harder masses of rock, which have successively resisted wear, may rise above the plain as residual mountains, just as they sometimes do in the peneplain of the normal cycle. What has been aptly termed land sculpture, by which is meant the bizarre shapes that rocks assume when acted upon by physical agencies, is due to the effect of varying gradations of hardness in the rocks. When a peneplain or plain of marine denudation is lifted high above sea level, without folding or steep tilting of the strata, streams are soon established upon the new land and proceed to cut deep trenches across the plateau. If the surface layers resist weathering, the plateau will be gradually dissected into flat-topped mesas and table mountains, which in the progress of denudation are converted into pyramidal shapes, while if the whole mass of rocks be easily destructible, they weather down into dome-shaped and rounded hills. The badlands are carved out of soft and scarcely inundated rocks, but firm rocks of climates of similar aridity give rise to many vertical-sided mesas, as is so notably the case in the sandstones of New Mexico. The Uinta Mountains in northern Utah are formed by a great anticlinal arch, so broad and gently curved that in a given section the strata appear almost horizontal. Out of these immensely thick and nearly level masses, the subaerial denuding agencies have carved an infinite and most picturesque variety of peaks, pinnacles, columns, and amphitheaters, while the streams have cut profound and gloomy canyons. The Grand Canyon of the Colorado is regarded as the most impressive example of this kind. Inclined or tilted strata give rise to a different class of topographical forms. If, as is generally the case, harder and softer strata alternate, the latter will be swept away more rapidly than the former, which are left standing as ridges or cliffs. As the inclination departs from vertical, the more unequal do the two slopes of each ridge become, the longer and gentler one being in the direction of the dip. Ridges and valleys of this class are beautifully exemplified in the Appalachian Mountains. At Kittatinny Mountain, through which the Delaware River has cut the famous Water Gap, the crest of the ridge is formed by very hard and indestructible sandstones and conglomerates, while the broad valley above and below the gap is in slates or other destructible rock. Where, however, the structure of a topography is tectonic in its character, where the strata are folded, ridges and valleys are necessitated, the ridges by anticlines and the valleys by synclines. If the folding be of moderate degree, so as to produce undulations of sweeping and gentle curves, the tendency of denudation is to reverse the original topography and convert the anticlines into valleys and the synclines into ridges. This apparently paradoxical result is found, when examined, to be natural and simple enough. The crests of newly formed anticlines have been subjected to tensile stresses which open the joints in the strata and render them very easy prey to the denuding agents. The surface of the synclines, on the contrary, has been tightly compressed, and their joints are closed by crowding. Volcanic topography is primarily constructive. The cones vary in form and height in accordance with the amount and character of the material of which they are composed, and the nature of the eruptions. Cones are first furrowed with ravines and valleys, and then gradually degraded into rocks or into low hills of volcanic agglomerate. The infinite variety of combinations of soft tuffs, loose masses of scoriae and ash, hard sheets, streams, pipes, and dikes of lava give rise to the manifold forms of volcanic mountains and islands in the course of denudation, the harder elements resisting longer and standing in relief. The Adirondack Mountains display a topography which is strongly dominated by streams of faults. Their general character is thus clearly described by J.F.O. Kemp. The Adirondack region is mountainous in its eastern half and has its highest peaks near its center, but on the west the mountains disappear and the area becomes a plateau ranging from 2,000 feet above tide gradually downward to the west until it is but slightly higher than Lake Ontario and the St. Lawrence. The mountains are arranged in visible northeast and southwest lines, and are often very steep, if not positively precipitous, in the portions that look to the southeast or northwest. There are also other steep faces nearly at right angles with the above, but they are less pronounced. These features are due to three intersecting systems of faults, the principal one of which is northeast and southwest, and determines the general trend of the mountains. The second system, which trends northeast at right angles to the first, is less important and acts chiefly in cutting the ridges into separate blocks. The third series, with north and south trends is quite subordinate in its effects. Faults frequently determine the location of valleys. The lower Hudson flows in a fault valley of which the Palisades form the scarp, and in the Adirondacks the drainage is so largely along intersecting fault lines that its regularity is very striking and has occasioned the descriptive term of lattice drainage. Brigham. The zigzag course of the Au Sable Chasm is determined partly by faults and partly by joints. The valley of the Rhine above Strasbourg is a great trough fault included between the Black Forest highlands on the east and the Vosges Mountains on the west. The most remarkable known instance of trough faulting is the Great Rift Valley of eastern Africa. The main valley continues northward from Lake Nyassa and contains Lake Rudolph and several smaller lakes, passing between the plateaus of Abyssinia and Somaliland. It extends to the Red Sea, which is itself regarded as being but a very deep part of the same great downthrow, inundated by the sea. At the northern end of the Great Sea, the Gulf of Aqaba, on the east side of the Sinai Peninsula, is an extension of the trough which, growing shallower, rises to the land and keeps its northerly direction for a long distance. Growing deeper again, it becomes the basin of the Dead Sea, the surface of which is 1,300 feet below sea level, and the valley of the Jordan, and north of that the valley of the Orontes, reaching nearly to Antioch. According to Seuss, this is not an erosion valley, but a tectonic depression. If this interpretation is correct, this vast dislocation extends through 50 degrees of latitude and is one of the most striking structural features of the Earth's surface. A river has its stages of development, youth, maturity, and old age, just as has a land surface, each stage displaying its characteristic marks. In a newly upheaved or newly folded land, the streams are determined entirely by the slopes of the new surface and are called consequent streams. As the river system becomes somewhat older, the stream channels are deepened, the larger ones being cut down to base level. And if the region be one of considerable elevation, deep gorges and canyons are excavated. A mature river system is characterized by the complete development of its tributaries and drainage, so that every part of its basin is reached by the ramifying channels. Valley floors are broadened and deposition begins upon them, and the streams, reaching a condition of equilibrium between erosion and deposition, are said to be graded. The final stages of river development are reached when the base level is attained and the drainage basin reduced to a peneplain by the combined action of the streams and weathering. As a river system approaches maturity, it will increase the number of its branches, and those branches which were not at all represented in the youthful stages of the system and are opened out along lines of yielding rocks are called subsequent. However the streams of a district may have been established in the first instance, whether they were consequent, antecedent, or superimposed, they are liable to changes more or less profound and far-reaching. The upstream extension of branches and the shifting of divides result in the capture of streams, or parts of such, by others more favorably situated, one master stream gradually absorbing many smaller ones which had originally been independent. Figure 30 shows two stages in the evolution of a river system. Figure 31 represents the first stage, in which several transverse streams, A, C, E, F, G, are breaching the escarpments indicated by these shaded lines. Of these streams, C carries the most water and will therefore deepen its gorges through the hard ridges more rapidly than the others and give its tributaries the advantage of the greater fall. In the second stage, C has captured the upper courses of all the other streams except G, which has not yet been reached. The branch 1 has captured A, beheading it, diverting the portion A double prime, and reversing the portion A prime. Similarly, M has captured and divided E. N has done the same with B and P with D, while G must eventually suffer the same fate. Wind gaps will be left in the ridges where the captured streams once crossed them. End of Chapter 12, Part 1. Section 23 of Science History of the Universe, Volume 2. This is the LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 2, edited by Francis Rolt Wheeler. Geology, Chapter 12. Physiography, Part 2. Coastlines are also of great physiographic importance. There is no greater mistake than to suppose the seacoast to be merely a line whereat the sea now washes. Yet it would be easy to find many people who would define the seacoast as being that stretch of land between high water and low water mark, with perhaps the addition of the former beach, in some cases, to the point of the beginning of land vegetation. Yet the coastline, truly speaking, may extend a long distance under the sea, and in a similar wise a wide range of marine beach formation may exist on land, even miles away from the sea. Regular coasts, says A. Penck, continue for great distances without notable indentations and, for the most part, in gentle curves, convex toward the land, which are connected by curved lines or meet at obtuse angles. The flatter the coast, the more perfectly is this type developed, and the coastline runs for many kilometers in the same curve. With a steep slope, the course is regular only in general. In detail, it seems as though drawn by a trembling hand, with numerous little prominences, which project but a few hundred meters beyond the general coastline, and separated from one another by shallow, curved indentations. The most conspicuous example of the irregular coast unquestionably is the fjord, seen in Norway and Scotland. They are irregular to a wonderful degree, possessing only this in common, that they are produced by the depression and submergence of the land surfaces, not by the throwing up of the high bluff, cliffs, and crags that remain. The fjords are long, narrow, frequently branched, and usually very deep. The ridges of land which separate adjoining fjords are frequently notched by low passes, which seaward become straits, connecting the fjords and cutting up the ridges into islands, which are always very numerous along coasts of this class. The famous Inside Passage from Puget Sound to Sitka, Alaska, is a network of deep waterways among countless islands. What are termed rias coasts have frequently been regarded as fjord coasts, but the bays here are shorter, more funnel-shaped, and not nearly so deep as fjords. Moreover, they are not of glacial origin, and hence are more widely distributed. Calais coasts are marked by numerous short, semicircular, and rather shallow bays, separated by narrow peninsulas, and owe their irregularities not to wave erosion, but to the submergence of land valleys. Those of the typical kind are due to the depression of mountain slopes furrowed by numerous short ravines. Faults are probably the cause of deep, lobate coasts, such as are to be found in Greece and in Haiti and Japan. There the bays are not so much irregularities in the coast line as deep gulfs, which have taken into themselves hundreds of square miles of land surface, and where the interlocking gulfs are of the same order of magnitude. The popular use of the word mountain is another snare. For example, there are many so-called mountains which are nothing more than the tops of the original plain, the whole of the surrounding country having sunk. A well-known example of this is the Grand Canyon of the Colorado, where, although there are cliffs and buttes of immense height from their bases, yet a line from side to side of the great gorge will reveal that none are greatly higher than the surface of the plain from which the river cut itself down. Some so-called mountain peaks and ridges are merely the portions of dissected plateaus left standing, such as Lookout Mountain and Missionary Ridge in Tennessee, and the Allegheny Front in Pennsylvania. A mountain range is made up of a series of more or less parallel ridges, all of which were formed within a single geosyncline or on its borders. The Appalachian Ridge, the Wasatch, the Coast Ridge are examples of typical mountain ranges. A mountain system is made up of a number of parallel or consecutive ranges formed in separate geosynclines, but of approximately similar dates of upheaval. The Appalachian system comprises the Appalachian Range, running from New York to Georgia, the Acadian Range in Nova Scotia and New Brunswick, and the Ouachita Range in Arkansas. Each of these ranges was formed in a different geosynclinal, but at the same geological date, and they are consecutive, having a common direction. A mountain chain comprises two or more systems in the same general region of elevation, but of different dates of origin. The Appalachian chain includes the Appalachian System, the Blue Ridge, the Highlands of New Jersey and the Hudson, a system of different date, and the tectonic system of western New England, which was not formed at the same time as either of the others. A cordillera consists of several mountain chains in the same part of the continent. Thus, the chains of the Rocky Mountains, Sierra Nevada, Coast Range, and their prolongations in Canada together make up the Rocky Mountain or Western Cordillera. From these definitions, it will appear that the mountain range has a unity of structure and origin which fits it especially for study. If the history of the ranges be understood, the systems and chains will offer little additional difficulty. The manner in which mountain ranges have been formed must be deduced from a careful study of their structure, for no one has ever witnessed the process of that formation. Mountain building may be going on at the present time. Indeed, there is no reason to suppose that it is not. But so slowly is the work carried on that it withdraws itself entirely from observation. Nevertheless, the general course of events may be inferred with much confidence from the structure of the range. The first step in the formation of a mountain range must evidently be the accumulation of an immensely thick body of strata. This, of course, must have taken place chiefly under shoal water, as thick strata can be accumulated only in rather shallow water and parallel with shorelines. To accumulate thick strata in shoal water, the bottom must subside as the sediments are piled upon it, else the water would be filled up and the deposition cease. Such a sinking trough is a geosyncline, and in geosynclines filled with sediments is the cradle of the mountains. The second stage in the building of a range is the upheaval of the thick masses of strata into a series of folds. This can be produced only by lateral compression, a conclusion which is sustained not only by the mechanics of folding and faulting, but also by the less obvious structures, such as cleavage and facility, metamorphism, the microscopic crumplings and plications, and the crushing and flowage of the mineral particles. The compressing force does not raise anticlines with great cavities beneath them, for such arches could not well be self-supporting, but mashes together the whole mass of strata, raising them into folds and wrinkles, crowding the beds into a greatly reduced breadth, or, when they are not sufficiently loaded to be plastic, breaking and dislocating them in a great thrust. It is not necessary to suppose that a mountain range was thrown up by one steady movement. On the contrary, there is good reason to believe that repeated movements, separated, it may be, by long intervals of time, have been engaged in the work. There are certain mountain ranges which have a different structure and must have had a correspondingly different mode of origin. As already pointed out, the Great Basin, which lies between the Sierra Nevada and the Wasatch Mountains, are a number of parallel mountain ranges with a prevalent north and south trend, which are collectively called the Basin Ranges. These mountains are not folds of very thick strata, but tilted fault blocks, which have been made by normal faults, each upthrow side standing as a great escarpment, but with a tilted top that gradually slopes back to the foot of the next block, to which it stands as the downthrow side. The process of denudation have carved these tilted blocks into peaks and ridges of the ordinary kind. Every mountain range has been profoundly affected by the agencies of denudation, and their ridges and peaks, their cliffs and valleys, have been carved out of swelling folds and domes or angular tilted fault blocks. The general character of the structure of the American continent is extreme simplicity, says Geikie, as compared with that of the Old World. In part of the Rocky Mountain region, for example, while the Paleozoic formations lie uncomfortably upon Precambrian gneiss, there is, according to King, a regular conformable sequence from the lowest Paleozoic to the Jurassic rocks, though probably many local unconformabilities exist. During the enormous interval of time represented by these massive formations, what is now the present axis of the continent appears to have been exempt from any great orogenic paroxysm, and to have remained hardly disturbed by more than a gentle and protracted subsidence. In the Great Depression or geosyncline thus produced, all the Paleozoic and a great part of the Mesozoic rocks were accumulated. At the close of the Jurassic period, the first great upheavals took place. Two lofty ranges of mountains, the Sierra Nevada, now with summits more than 14,000 feet high, and the Wasatch, 400 miles apart, were pushed up from the great subsiding area. These movements were formed by a prolonged subsidence, during which the Cretaceous sediments accumulated over the Rocky Mountain region to a depth of 9,000 feet or more. Then came another vast uplift, whereby the Cretaceous sediments were elevated into the crests of the mountains, and a parallel coast range was formed fronting the Pacific. Intense metamorphism of the Cretaceous rocks is stated to have taken place. The Rocky Mountains, with the elevated tableland from which they rise, now permanently raised above the sea, were gradually elevated to their present height. Vast lakes filled depressions among them, in which, and on the plains in front of the mountains, as in the tertiary basins of the Alps and the Gondwana series of the Himalaya, enormous masses of sediment accumulated. The slopes of the land were clothed with an abundant vegetation in which we may trace the ancestors of many of the living trees of North America. One of the most striking features in the later phases of this history was the outpouring of great floods of trichyte, basalt, and other lavas from many points and fissures over a vast space of the Rocky Mountains and the tracts lying to the west. In the Snake River region alone, the basalts have a depth of 700 to 1,000 feet over an area 300 miles in breadth. End of chapter 12.
Section 24 of the Science, History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 2, edited by Francis Rolt Wheeler. Geology, Chapter 13. Historical Geology, Part 1. While the life history of organisms is truly biology, and the life history of extinct forms of animals belongs largely to paleontology, yet the geologist has an intimate relation to both, to the life history of present organisms because of their effects upon the Earth's surface, and to the relics of past organic life, because their presence in certain rocks reveals the conditions that prevailed when those rocks were laid down. Historical geology, says Geikie, deals with fossils or organic remains preserved in natural deposits and endeavors to gather from them information as to the history of the globe and its inhabitants. The term fossil, meaning literally anything dug up, was formerly applied indiscriminately to any mineral substance taken out of the Earth's crust, whether organized or not. Ordinary minerals and rocks were thus included as fossils. For many years, however, the meaning of the word has been so restricted as to include only the remains or traces of plants and animals preserved in any natural formation, whether hard rock or loose superficial deposit. The idea of antiquity or relative date is not necessarily involved in this conception of the term. Thus, the bones of a sheep buried under gravel and silt by a modern flood and the obscure crystalline traces of a coral in ancient masses of limestone are equally fossils. Nor has the term fossil any limitation as to its organic grade. It includes not merely the remains of organisms, but also whatever was directly connected with or produced by these organisms. Thus the resin which exuded from trees of long perished forests is as much a fossil as any portion of the stem, leaves, flowers, or fruit, and in some respects is even more valuable to the geologist than more determinable remains of its parent trees, because it has often preserved in admirable perfection the insects which flitted about in the woodlands. The burrows or trails of a worm in sandstone or shale claim recognition as fossils, and indeed are commonly the only indications to be met with of the existence of annelid life among old geological formations. The droppings, coprolites, of fishes and reptiles are excellent fossils, and tell their tale as to the presence and food of vertebrate life in ancient waters. The little agglutinated cases of the caddis worm remain as fossils in formations from which perchance most other traces of life may have passed away. Nay, the very handiwork of man, when preserved in any natural manner, is entitled to rank among fossils, as where his flint implements have been dropped into the prehistoric gravels of river valleys, or where his canoes have been buried in the silt of lake bottoms. The term fossil, moreover, suffers no restriction as to the condition or state of preservation of any organism. In some rare instances, the very flesh, skin, and hair of a mammal have been preserved for thousands of years, as in the case of mammoth carcasses entombed in the frozen mud cliffs of Siberia. Generally, all or most of the original animal matter has disappeared, and the organism has been more or less completely mineralized or petrified. It often happens that the whole organism has decayed, and a mere cast in amorphous mineral matter, as sand, clay, ironstone, silica, or limestone, remains. Yet all these variations must be comprised in the comprehensive term fossil. The conditions of the preservation of fossils, says Scott, are much more favorable to some kinds of organisms than to others. It is only under the rarest circumstances that soft gelatinous animals, which, like jellyfish, have no hard parts, can leave traces in the rocks. The vast majority of fossilized animals are those which have hard shells, scales, teeth, or bones, and of plants, those which contains a sufficient amount of woody tissue. Again, the conditions under which organisms live have a great influence upon the chances of their preservation as fossils. Land animals and plants are much less favorably situated than are aquatic forms, and since the greater number of sedimentary rocks were laid down in the sea, marine organisms are much more common as fossils than are those of fresh water. On land, fossils have been preserved, sometimes in astonishing numbers, under wind-made accumulations of sand, dust, or volcanic ash, and in the floodplain deposits of rivers. Peat bogs are excellent places for fossilization, and the coal seams have yielded great numbers of fossils, principally of plants. The remains of land animals and plants, especially of the latter, are sometimes swept out to the sea, sink to the bottom, and are there covered up and preserved in the deposits. But such occurrences are relatively uncommon. Small lakes offer more favorable conditions for the preservation of terrestrial organisms. Surrounding trees drop their leaves, flowers, and fruit upon the mud flats. Insects fall into the quiet waters, while quadrupeds are mired in mud or quicksand and soon buried out of sight. Flooded streams bring in quantities of vegetable debris, together with the carcasses of land animals drowned by the sudden rise of the flood. The great series of freshwater and volcanic ash deposits, which for long ages were formed in various parts of our West, have proved to be a marvelous museum of the land and freshwater life of that region. On the fine-grained shales are preserved innumerable insects and fishes, with multitudes of leaves, many fruits, and occasionally flowers, while in the sands, clays, and tufts are entombed the bones of the reptiles, mammals, and more rarely, birds of the land, mingled with those of the crocodiles, turtles, and fishes that lived in the water. Similar deposits are known in other continents, but it is on the seabed that the conditions are most favorable to the preservation of the greatest number and variety of fossils. Among the littoral deposits, ground by the ceaseless action of the surf, fossils are not likely to be abundant or well preserved, but in quieter and deeper waters, vast numbers of dead shells and the like accumulate and are buried in sediments. A geological chronology, says Scott again, is constructed by carefully determining, first of all, the order of superposition of the stratified rocks, and next by learning the fossils characteristic of each group of strata. To many it has seemed that this is reasoning in a circle, but that is because the argument is not fully stated, some of its steps being omitted. The order of succession among the fossils is determined from the order of superposition of the strata in which they occur. When that succession has been thus established, it may be employed as a general standard. Great physical events, such as the upheaval of mountain ranges, widespread transgressions of the sea, and changes of climate, often provide a means of correlating the strata of different continents with greater precision than can be done with the aid of fossils only. The latter are, however, indispensable means of first determining which of these events are comparable in different regions. The history is recorded partly in the nature and structure of the rocks, partly in the fossils, and partly in the topographical forms of the land and the courses of the streams. By combining these different lines of evidence, local histories are constructed for each region, until from these, the story of the whole continent may be compiled. The comparative study of the fossils then gives the clue for uniting the history of the different continents into the history of the earth. The method of making the divisions and subdivisions of geological time is not yet a fixed one, and there is much difference in the usage of various writers. The names of the divisions also have been given at various times and in many lands, according to no particular system. Most of these names have been taken from the locality or district where the rocks in question were first studied or are most typically displayed, as Devonian from Devonshire, Jurassic from the Jura Mountains. Some are named from a characteristic or prevalent kind of rock, such as Cretaceous, Latin Creta or chalk, and Carboniferous. Of late, there has been a tendency toward a more uniform method of nomenclature and to the use of one set of terms for the divisions of time and another, and corresponding set for the divisions of the strata. The following table represents the divisions of the scale of time and the scale of rocks, which have been adopted by the International Geological Congress. Time scale: era, period, epoch, age. Rock scale: group, system, series, stage, substage, zone. It will be observed that the subdivision is carried farther in the scale of rocks than in that of time, because of the generally local character of these minor subdivisions. The names employed are, as yet, the same for both scales, and we speak of the Paleozoic era, or group, and of the Silurian period, or system. It has been proposed to give separate names to the divisions of the two scales, and this would be an improvement in some respects. Table of major geological divisions. Cenozoic era, Quaternary period, Tertiary period. Mesozoic era, Cretaceous period, Jurassic period, Triassic period. Paleozoic era, Permian period, Carboniferous period, Devonian period, Silurian period, Ordovician period, Cambrian period. Precambrian eras, Algonquian period, Archean period. Tracing the history of mankind back to very ancient times, records become more and more scanty and less intelligible until history fades into myth and tradition. Of a still earlier age, there is not even a tradition. It is prehistoric. Similarly, among the geological records, the earliest are in a state of such excessive confusion that they are exceedingly difficult to understand, and between different observers, there are radical differences of opinion, both as to the facts and as to their interpretation. Furthermore, there must have been an inconceivably long time earlier than the most ancient recorded periods, as to which conjecture and inference are the only resource. In these difficult straits, astronomy offers valuable assistance to the baffled geologist. The nebular hypothesis is a scheme of the development of the solar system, which is generally accepted by astronomers in some form as essentially true. The term nebular hypothesis is usually, though not with exactness, limited to one particular form, according to which the place of the present solar system was originally occupied by a vast rotating nebula, a mass of intensely heated vapor, or possibly clouds of meteorites, extending beyond the orbit of the outermost planet. As the nebula cooled by radiation, it contracted, leaving behind it successive rings, like those of the planet Saturn, but on a vastly larger scale. The rings kept up the rotation imparted by the nebula, and all of them lay in nearly the same plane. Unequal contraction in various parts of each revolving ring caused it to break up and gather by mutual attraction into masses. If these rings were composed of relatively small solid masses, like meteorites, or if they had solidified by condensation of the vapors, the heat generated by the collision, as the broken ring was gathered into a mass, would suffice to raise the temperature and liquefy or vaporize the mass. By revolution, the nebulous masses would assume a spheroid shape and become planets. The central mass of the original nebula forms the Sun, which is still in its intensely heated, incandescent state. Another form of the nebular hypothesis, called for the sake of distinction the planetesimal hypothesis, has recently been proposed by Professor Chamberlain. This postulates, as the beginning of the solar system, a spiral nebula, and that the matter of this parent nebula was in a finely divided solid or liquid state before aggregation. It regards the knots of the nebula as the nuclei of the future planets, and the nebulous haze as matter, to be added to these nuclei to form the planets. It assumes that both the knots and the particles of the nebulous haze moved about the central mass in elliptical orbits of considerable but not excessive eccentricity. It deduces a relatively slow growth of the Earth, with a rising internal temperature developed in the central parts and creeping outward. From the strictly geological standpoint, the most important difference between the nebular and the planetesimal hypotheses is that, according to the former, the Earth has passed through a gaseous and a molten stage, and therefore must have formed a crust by solidification, while the latter leads to the conclusion that the Earth has been solid from the beginning, and consequently never formed a crust of solidification. It is unfortunate, says W. B. Scott in his Introduction to Geology, Macmillan Company, that an account of historical geology should begin with the most difficult and obscure part of the subject, but the treatment must be in accordance with the chronological order, and the oldest rocks are the least intelligible. The ordinary criteria of the historical method, namely the stratigraphical succession and comparison of fossils, fail us here almost entirely, and the only way of correlating the rocks of different regions and continents is by means of the characters of the rocks themselves. In the present state of knowledge, lithological similarity is not a safe guide. So many metamorphic rocks, once referred to the Archean, have proved to be of much later date that some cautious geologists, who have no confidence in lithological similarities, prefer not to use the term Archean at all, but to employ local terms for the oldest crystalline rocks exposed in a given district. The Archean includes the most ancient rocks, often spoken of as the basement or basal complex. Its antiquity is best assured in regions where it is separated by thick series of sedimentary or metamorphic rocks from the lower Cambrian, which can be certainly identified by its fossils. The Archean is composed of completely crystalline rocks of various types, massive rocks such as granite and basic eruptives, and foliated rocks like gneissoid granite, gneiss, and many varieties of schists, are intermingled in the most intricate way, a characteristic well expressed in the oft-used phrase of the basal or fundamental complex for the Archean. The component mineral particles show plainly the intense dynamic metamorphism to which they have been subjected in their extremely complex arrangement and in their laminated and crushed condition. The rocks thus referred to the Archean are not necessarily all of the same age, but they are all of vast antiquity and older than any other known series. They are of very great but unknown thickness, for the bottom of them is nowhere to be seen, and even when thrown up into mountain ranges, erosion has in no case cut so deeply into these rocks as to expose anything different below them. The origin of the Archean rocks, Scott resumes, is a problem which has given rise to a great deal of discussion, but a solution appears to be near. Independently, in many countries, observers have reached the conclusion that these rocks are divisible into two great series, a schist series composed chiefly of highly metamorphosed sedimentary and volcanic rocks, and a gneissoid granite series, which is intrusive and later than the former. Assuming that this conclusion is true, at least as a working hypothesis, it involves certain curious consequences. Surface lava flows and volcanic tuffs, and still more sedimentary rocks, necessarily imply a solid floor upon which they were laid, but of this floor not a trace has anywhere been found. The question immediately arises, what has become of it? No answer to this question can yet be given, but apparently the most likely suggestion is that the ascending floods of molten magma, which gave rise to the gneissoid granites, must have melted and assimilated it. If this were only a local phenomenon, there would be nothing very surprising about it, but it would seem to be true of the entire globe, and this is a startling conclusion. It would appear then that a solid crust, however formed, was for a very long time sufficiently rigid and stable to allow a great thickness of sedimentary and volcanic rocks to be accumulated upon it, and then was engulfed and destroyed by a universally ascending magma, though it is not necessary to suppose that this took place simultaneously over the whole earth, or even within a relatively short period of time. It may have required ages in the accomplishment. Furthermore, it must not be forgotten that remnants of the floor may yet be discovered in little-known regions. If this complete and universal assimilation actually took place, it is an absolutely unique phenomenon in the recorded history of the earth, though something more or less similar may have happened many times before that record began. The present writer is not entirely in agreement with Professor Scott as to the following division of geologic time, but in view of the fact that the sequence used in this summary is taken from his Introduction to Geology, no change will be made in the order of presentation. The Algonquian is the name proposed by the United States Geological Survey for the great series of sedimentary and metamorphic rocks which lie between the basal Archean complex and the oldest Paleozoic strata. It is but little used outside of this country and is not universally employed even here, but it is beginning to make its way in Europe and serves a useful, though possibly a temporary, purpose. While it is possible, though not very likely, that more advanced knowledge may make it possible to distribute these rocks partly into the Archean and partly into the Paleozoic, yet for the present at least, it is better to form a separate grand division for them. The Algonquian rocks, which are widely distributed in North America, form an immensely thick mass of strata and of metamorphic rocks, which are believed to represent those strata in other regions. These metamorphic rocks were long generally referred to as the Huronian, which was regarded as the upper portion of the Archean, but so far as can be learned, they occupy the same stratigraphical position as certain little changed sediments between the fundamental complex below and the Cambrian above. At the base of the magnificent section exposed in the Grand Canyon of the Colorado is a very thick mass of strata, separated by great unconformities from the Archean gneiss below and from the overlying Cambrian. This mass is again subdivided by minor unconformities into three series. The lower series, at least 1,000 feet thick, and perhaps more, is made up of stratified quartzites and semi-crystalline schists cut by intrusive granite. Above this come nearly 7,000 feet of sandstones with included lava sheets, and at the top more than 5,000 feet of shales and limestones, in which a few fossils have been found. The two upper series are not at all metamorphic. All these strata are steeply inclined, and upon their truncated edges rests the sandstone referred to by Mr. Walcott to the Middle Cambrian. End of section 24.